Assalamualaikum warahmatullahi wabarakatuh. My name is Wan Sharil Adam Bimasri and I'm here to discuss ocean ion fertilization. This presentation is part of the Planktonology MMB3323 courses. Okay, next, what is an OIF? OIF, or commonly known as ocean ion fertilization, is defined as the artificial addition of iron to iron limited to the high nutrients, low chlorophyll HNLC regions. The purpose of this is to stimulate oceanic carbon sequestration through the biological pump. Next, ancient ocean ion fertilization. It analysis of trapped air bubbles in Arctic and Antarctic ice cores have revealed significant insight into past climate conditions. During the last glacial maximum around 20,000 years ago, atmospheric carbon dioxide levels were approximately 180 parts per million. This is considerably lower than the pre-industrial level of about 280 ppm. Next, Martin's hypothesis development. The link between iron, dust, and carbon dioxide level was hypothesized by John Martin. During the last glacial maximum, increased dust inputs relieve iron limitation in HNLC regions, especially in the Southern Ocean. This enhanced the biological pump which drew down atmospheric carbon dioxide. Martin's hypothesis suggests that glacial period dust flux acting as an iron source play a role in reducing carbon dioxide level. Next, primary goal of OIF. The primary goal is to test whether iron addition can induce significant carbon export flux below the winter mix layer depth MLD for long-term storage, thereby mitigating atmospheric carbon dioxide levels. Experiments are aimed to quantify the effectiveness of iron-induced carbon export and assess any ecological impact. The next area of interest. The areas of interest for ion fertilization that are commonly done are the subarctic North Pacific, the equatorial Pacific, and the Southern Ocean. These are high nutrient, low chlorophyll HNLC regions. In these areas, phytoplankton cannot fully utilize the available micronutrient because they lack iron. This results in a relatively low primary production. Despite the high availability of micronutrients, scientists and industries are interested in these regions to test whether adding iron can stimulate phytoplankton growth, enhance carbon sequestration, and potentially reduce atmospheric carbon dioxide levels. Okay, next, the importance of OIF. OIF can give a big impact to the climate change. How? Okay, when there is a high iron availability in HNLC regions, it releases iron limitations, substantially enhancing the biological pump. This process increases carbon fixation and subsequent export to the deep oceans, reducing atmospheric carbon dioxide level. Conversely, when iron is limited, the biological pump is less effective, leading to lower carbon sequestration and potentially higher atmospheric carbon dioxide concentrations. OIF experiments to date, until now, 13 artificial OIF or AOIF experiments have been performed since 1990 in HNLC regions. Limitations to these studies, except in the Southern Ocean, European iron fertilization experiment effects no significant change in the effectiveness of artificial OIF. The amount of iron-induced carbon export flux below the winter mix layer depth (MLD) has been detected. The successfulness of OIF experiments. These artificial OIF field experiments have demonstrated that primary production can be significantly enhanced by the artificial addition of iron. However, except for effects, the experiments have not achieved their main aim of removing carbon from the atmosphere and increasing carbon sequestration. Okay, next, the future of OIF experiments. To increase the success rate of OIF experiments, we need to use the effective methods. Based on past experiments, the following methods are crucial for effective ion fertilization. Number 1, experiment location. Conduct experiments in the center of an eddy structure when grazing pressure is low and silicate levels are high. Example, in the South Ocean, south of the polar front during early summer. Next, shipboard observations. Extend observation over a minimum of 40 days with multiple ion injection, at least 2 or 3 ion infusion of around 2000 kg with an interval of 10 to 15 days to fertilize a patch of 300 km per square and obtain a 2 nanomoles concentrations. Number 3. Tracing the iron fertilized patch. Use both physical, example drifting buoy, and biogeochemical, example sulfur has sulfuride, photosynthetic, photosynthetic quantum efficiency, and partial pressure of carbon dioxide traces. Next, number 4. The sediment traps and thorium method. Employ neutrally buoyant sediment traps (NBST) and apply the water column derived thorium-234 method at 2 depth. Example, just below the in situ MLD and at the winter MLD, with autonomous profiler equipped with an underwater video profiler UVP and a transmissometer. And this is my list of references. And I think that is all from me. Thank you.